Hello, this is Danu, and today we are returning to the classification problems and will briefly discuss about a powerful algorithm called support vector machines, or SVMs for short. The presentation slides and source codes I use here were obtained from the Intel Machine Learning course. I reorganized the contents for easy understanding. You can download the original content from the website using the link. Let's get started. So here's the example we discussed in the previous video, which predicts the survival likelihood of a new patient. Let's imagine an optimal line that separates the two classes. We can imagine some possible lines. Not this one. There are many misclassifications. Not this one either. This line looks good. Can you imagine a better line? And yes, this line looks perfect. The line's left is blue and the right is red. How can we obtain the line from input training data? The idea is to draw the line at every place with an equal distance from the closest blue and red. The blue and red samples that touch the dotted lines are named support vectors. They maximize the distance margin between the two classes. Using each class's support vectors, we mathematically find the optimal line by minimizing the cost function j of beta as we did in linear regression. Specifically, the beta 1 and beta 2 represent the vector orthogonal to the optimal line. Okay, now that the best decision line we've found looks fine. But what happens when the dataset gets tricky? Take a look at this example. An outlier red sample is placed very close to the blues. If we want to classify the outlier red correctly, the line should be changed like this. But it looks overfit. Therefore, this is still the best separating line. We can achieve this situation mathematically by adding a penalty term in the cost function and minimizing the j function. The added penalty is called a regularization. It regularizes that the cost becomes higher to classify the outlier red correctly than moving the decision line. If you want to learn more about the regularization, please refer to the original content of Intel. We've seen the linear version of support vector machines so far. Now let's dive into a kernel version of SVMs that solve nonlinear decision boundaries, as shown in the left figure. With the so-called kernel trick phi function, we can map the complicated nonlinear curve into separable cases in three-dimensional space. A nonlinear curve in the original space can be mapped into a linear line in the transformed space. This transformation forms a higher dimensional space. For example, it transforms two-dimensional space into three or more dimensions to find a linear separation case. Let's briefly examine two kernel ideas. Here's a dataset about movie budgets and user ratings. Not linearly separable. Two classes were colored blue and red and represented in two-dimensional space. The first idea is to create additional features from the original two features to transform the idea, such as budget squared, ratings squared, budget times rating, and so on. The second idea is to transform the space into a different coordinate system. It is a more popular approach. The kernel defines the mapping. First, the algorithm selects the support vectors. Suppose three movies, Transformers, Black Swan, and Pulp Fiction are selected. Then, we create a new feature for each movie using the Gaussian function. For input data sample X in rating and budget 2-dimensional space, we calculate the distance between X and the transformer using the Gaussian function. It is the first new feature, A1. The Gaussian distance between X and the black swan becomes the second new feature, A2. The third feature, A3, is the Gaussian distance from Pulp Fiction. In this way, we map the data in 2-dimension into 3-dimension by creating 3 new numbers using these 3 Gaussian distances. We call this method the Gaussian kernel. And now we can find a linear plane that classifies movies nicely. It is easier to classify data in a new, higher dimensional space. We can also create new features using the radial basis function, also known as RBF. This is called the RBF kernel. You can check the original Intel content for more information about the RBF kernel. So SVM has shown powerful classification performance because of its mathematical rigors. However, in real-life problems, detecting support vectors, applying the kernel for every input point, every data point, and finding the optimal line takes a long time and a lot of work to train. In practice, we take approximate approaches to kernel mappings using sampling to reduce the computational cost. Nystrom or RBF sampler are another popular kernel approximations. We do not mention the details because they are beyond this tutorial. And that's all I prepared for this video. Thank you for listening and see you in the next video. Bye.